So can you see the screen?
Yes.
Okay, so this is where we stopped last time. We were looking at system task and we saw the system task related to files, file opening, file closing, and writing to files.
Yeah.
So any questions related to any of those tasks or any other thing?
No.
We'll go forward. Today we're going to see how to write test benches using Verilog. So we have seen now for a while how to write Verilog designs or how to describe various circuits using Verilog language. Once you write a Verilog design or once you describe a circuit using Verilog language, you would like to test it to see whether the digital circuit works correctly as per the expectations or not. So how do you do that? You write a test bench, that too in Verilog language. And using the test bench, you test your design for the functional aspect of the design. So uh, the way it works is you might have used various boards, for example, in your electronics labs or embedded labs. And to test the logic on the board, you apply the inputs to the board using signal generators or some other mechanism. And the board will generate certain outputs. Those outputs have to be monitored. So those outputs are monitored using a oscilloscope or a digital logic analyzer or could be multimeters or could be other mechanisms. So you apply certain inputs to your board. The board, according to its logic or according to its circuit, will use and process that inputs, and some outputs will be generated. So you monitor the inputs and you monitor the outputs. You already know the logic of your board. So you analyze whether, based on the current set of inputs, are the outputs that are generated, are they correct or not? You analyze that. And based on that, you say, yes, my board is working correctly or there is a problem with the board. So similar concept we are going to apply with a Verilog test bench, where the design that you have created is called the design under test or DUT. We will apply some inputs to the design, and based on the logic of the design and the current inputs, it will generate some outputs. So we monitor the inputs, we monitor the outputs that are generated. That is called, we generate something called a timing diagram, and we analyze the timing diagram. If the for current set of inputs, if correct outputs are generated, then we say that my design is working as per expectations or my design is functionally verified. Okay, so that is what we will achieve using test benches. So how to write a test bench and how to apply inputs we'll see in this section. So this is what you have it. This test bench is another Verilog design or Verilog file module for that matter, under which we are going to instantiate the design under test. So we saw structural modeling techniques where we created small components first or small modules, and those modules were instantiated under the bigger module. The bigger module will instantiate one or multiple small modules, and it will create a hierarchical design. The same concept, we are going to use a top level of the design, whatever the top level is. That top level of the design will be instantiated under the test bench module. In the test bench module, we are going to apply stimulus or inputs to the design under test, which is the top level of the design. So based on the inputs given and based on the logic of the design, it will generate some response or generate some outputs. At the test bench level, we will monitor the inputs, we'll monitor the outputs. This will generate a timing diagram for us. And based on that timing diagram, we'll analyze that timing diagram. If the outputs generated are correct as per the inputs and the logic given, we say that my design is functionally verified. So how does this work? The circuit description is your Verilog design. Test bench is also a Verilog module. We apply both to something called a Verilog simulator. The simulator will simulate both the design and the test bench and will generate timing diagram, which is the result. We analyze that. If there is a problem, we keep fixing it. So if there is a problem in the design, we fix the error in the design. If there is a problem in the test bench, we fix the error in the test bench. and we'll do another iteration of this whole process. And we'll keep doing this till we get the correct result. Here. So test benches are useful for simulation and verification. So the test bench module that you're going to write will never be synthesized. So if you're working on FPG or ASIC, the test bench will never go, or the testing environment will never go on the chip. It's only the design that will go on the chip. Test bench is a testing environment that is used for verification purpose at simulation or software level verification level. Uh, for test bench purpose, we have seen that certain part of Verilog is synthesizable. Means only certain sections of Verilog can be used for designing a circuit that has to be implemented on a chip. For a test bench, there is nothing going to be implemented on the chip for the test bench part of it. So entire Verilog language is available to you to be used in the test bench. Whatever is part of Verilog language can be used in test benches. For example, hash delays. I cannot use hash delays directly in my design. I can using clock I can build delays and timers, but I cannot directly use hash delays in the design. But in the test bench, I can use hash delays based on the time units declared. So time unit will be declared using the tick time scale directive, as we saw last time. Almost last time. Dollar display. So anything with a dollar sign is basically a system task. The system task is used for simulation purpose. Since we are going to use test benches for simulation, any system task can be used. Tick time scale will define the time scale. So the first thing that you do in a test bench is define a time scale. Because I'm going to be simulating my test bench, for simulation the time scale is critical. So we have to declare a time scale for the test bench and for the entire design. So let's say this is a top level test bench under which I'm going to instantiate the top level of the design and then apply inputs and outputs to it. This is my top level of the design, which has block A, block B as a sub blocks to it. So this is my module top, which I'm going to. Did we cover this by any chance? I feel like we have covered this.
Yes, we have.
I think we went up to this, right? Module analysis, if I remember it.
Yes.
So analysis was a module, and we instantiated analysis module. We did a dollar monitor on it, and then we monitored this.
Mm-hmm.
I think this is where this part is already covered. I think.
Yeah.
Okay. So inline stimulus. So stimulus can be applied. In that case, we'll cover this part. So stimulus can be applied in various ways, or inputs can be applied in various ways. To initial block or sometimes to always block. There's something called inline stimulus. So let's look at the example of inline stimulus. Take time scale 1 nanosecond slash 1 nanosecond. This is my time scale. This is my precision of the simulation.
Mm-hmm.
Module inline TB for test bench. So there is this test bench is always empty ports. There are no ports declared for the test bench because this itself is the stimulus provider to the design. I declare local registers and wires, and there is a DUT design under test instantiated here, and we are doing a port mapping. In this case, we are using the shortcut method for the port mapping, directly mapping the actuals without using the formulas. So this is the module instance where I'm and then port mapping of the instance. Now this initial block is where I'm going to apply the stimulus. Begin the initial block. Hash 10 into 1 nanosecond. So after 10 nanoseconds, address is equal to 8 tick H01. So I'm applying the 8-bit hex value 01 to address, which is 8 bits here. You see, ADDR is address 8 bits. Then after another 10 nanosecond, data bus will get hex value 23. After another 20 nanosecond, data bus will change to hex value 45. After another 30 nanosecond, address will change to hex value 67. Another 30 nanoseconds, data bus will change to 89 hex value. Another 40 nanoseconds, data bus will change to AB hex value. Another 45 nanoseconds, I wait and I do dollar finish, which is a system task to end the simulation. So it will stop the simulation at this point, end the initial block, end module. So If you see here, we are applied inputs in line one after another. That's why it's called an inline stimulus test. Normally, you will see that the test bench will become very long because we are going to apply various inputs one after another in line. But it is easy to define complex timing relationship between signals. So if you have very specific timing requirements, like after so many nanoseconds or whatever the timeline is, the one of the inputs need to change. Then after another few nanoseconds, the other inputs have to change. This can be controlled rather easily by directly using the hash keys. This doesn't have to be round numbers, it can be any number. It can be, for example, hash 11. This can be hash 23. This can be hash 35 or any other number. So any complex timing relationship between signals can be managed rather easily using this technique. And you list the variables only when their values change. Any other variable is not mentioned. Only the one which or the register which values will change are mentioned here. But one of the key disadvantages with this technique is now this is a very small example, but imagine having multiple input output ports. Now you will have so very long test bench in that case if you apply this method of stimulus application. So to get around that, you can use some other syntax available in Verilog. For example, for loops. How do we use that? Take time scale 1 nanosecond slash 1 picosecond. So I can precision is up to 1 picosecond level in this case. So
Mm-hmm.
I can zoom in my simulation up to 1 picosecond window in this case. Module loop test bench, empty ports. Wire 7 down to 0 response, red 7 down to 0 stimulus. There is a clock requirement in this case. So reg clock initial value is 0. There is an integer called I. Now this is my design under test which I am instantiating just like last time. Initial begin the block. For I equal to 0, I less than equal to 255, I equal to I plus 1. So 0 to 255 means 256 times the for loop will execute. What am I doing inside the for loop? At negate clock, stimulus is equal to I. On every negate of clock, I value, which will be increments of I value, this loop index, will be applied to
Mm-hmm.
stimulus, which is a register declared here, 8-bit register. After the for loop is over, I wait for another 20 nanoseconds because that's my timeline, time scale declared here. I wait for another 20
Mm-hmm.
nanoseconds. After the for loop is over, then I finish my simulation or stop my simulation. End the initial block. But we have a always block. Why? Because there is a clock requirement. We are checking for neg age of the clock in this for loop, but the clock is not generated. The clock is generated in this always block. Always begin the block. Always there is no sensitivity list, so the always block will always execute without waiting for anything. Begin the always block. Hash 10 means hash wait for 10 nanoseconds. Clock is equal to 1. Wait for another 10 nanoseconds. Clock is equal to 0, and this will keep repeating because it's a always block with no sensitivity list. Means I will get a free running clock. This means that I'll get a free running clock, continuously generated clock using this always block. And this clock will be the negative edge of this clock signal will be sensed here in the initial block, and on that negative edge of the clock the stimulus will be applied.
Yeah.
The initial block and the always block work concurrently with respect to each other. They are parallelly executed with respect to each other.
Okay.
So this way, you have applied actually 256 inputs, but the test bench is rather compact in this case. Whereas in case of inline stimulus, imagine doing this 256 times. So this itself would have created 256 lines in the test bench. So compared to this method, inline stimulus method, this method will give you more compact test bench. Okay.
Okay.
Yeah, so we can even use task in case of this. There is an example of task. So we are not declaring, we are only looking at a task where this particular timing diagram is generated or this signals are generated. The other module declarations and other thing we are bypassing for now. Only the task is used, is seen here, which will help me generate this timing diagram, which is a requirement in the test bench. So if you see here, data valid is a signal from 0 to 30 nanosecond, it stays 0. From that point, after another 20 nanoseconds, at 50 nanoseconds, the CPU data, which was tri-stated earlier, gets data in value. And the data in stays valid from 50 nanoseconds to 70 nanoseconds, that is for 20 nanoseconds. Again, it is tri-stated. The ZZ means it's tri-stated. And at 70 and 50 nanosecond to 70 nanosecond duration, I get another pulse here called data read, which is high or active during those 20 nanoseconds. It will go low before that and low after that. So in this 20 nanosecond window, it's high. And the same window, the data in is a valid data on CPU data. Then data valid stays high for another 30 nanoseconds, till 100 nanoseconds, then it goes low. So now I have to write a task to generate this timing diagram behavior. How do I do that? Task CPU read. Begin the task. Hash 30. So let's assume timescale is 1 nanosecond. Hash 30 will give me 30 nanosecond delay. Data valid is equal to 1. So data valid will be 0, and after 30 nanosecond data valid is 1. So after 0 to 30, at 30 data valid becomes 1. Wait till data read is equal to 1. So wait till data read is high. I will wait till data read is high. From 30 to 50 I will wait. Once data read is high, CPU data gets data in. So once this high comes on data read signal, CPU data, which was tri-stated, will get data in value here at this point, 50 nanosecond point. After that, wait till data read is 0 is equal to 0. So data read went 0 at this point, 70 nanoseconds. We sense this edge. At that point, CPU data was again tri-stated. 8 tick HZZ means 8-bit tri-stated value. CPU data will get 8-bit tri-stated value at this point. Wait for another 30 nanoseconds, then make data valid equal to 0. From this point, I waited for another 30 nanoseconds. Then data valid went to, or data valid was pulled down to logic 0 here. And this begin end task. So this task is giving me this timing diagram behavior. And this task can be called in the module in the always block or initial block of a test bench module rather, in the initial block or the always block. Normally it's called in the initial block because you apply the inputs once properly. So it will be called in the initial block, and which will generate this timing diagram. So the point is we can use task and delays inside the task in the test bench for our test vector application or stimulus application. Do you understand this? Any questions related to this?
No.
Okay, so I'll give you some time to note down few of these things, and then we can move forward. So inline stimulus, I don't think you need this slide, but inline stimulus you can note down, and the next couple of slides.
Okay. I'm done with this.
Yeah, that's fine.
I'm done.
Fine.
I'm done.
Mm. So next part is we saw tick include. So tick include was a compiler directive that could be used to include various other files. For example, if you compare this to C language or embedded C programming, there is something called hash include, through which you can include other header files or other C files. So the tick include is basically the similar concept. Let's say there is a package.v file where we are declaring all the common definitions, time, and anything common is declared under this package file. And this package file is included in the module in the using the tick include directive. So this package.v file has tick timescale declaration, tick defined. So period is a constant defined using tick defined. Value is 20. Timeout is a constant using tick defined. This is the value. So period and timeout are then used here in the module because we are including the package.v file. Tick include double quotes package.v double quotes. This means this package.v file should be located in the same directory where this particular module or this particular Verilog file is getting saved. Then you will find it there, or you can give a relative path to this directory. So this is included here, and then the rest of the module can be whatever logic you want to declare. Any definitions made here in this package is accessible inside the module. So for example, tick define period means I can use tick period here. Tick define timeout means I can use tick timeout here. This is my module where I'm accessing these various things. This could be common declarations for which I can declare a common package file. That's how tick include works. If you remember, we saw this I think during the start of the training program. This is the design flow or the design methodology for Xilinx FPGAs. So this is where just before Verilog description, this is a place where you define the design specifications. So what are the how do I want to do my design? What is expected out of my design? All that is part of my design specifications. For that design specification, I start writing Verilog code, or I start describing the design in Verilog language. Once my design is complete, I would like to test it. So how do I do that? I write a test bench also in Verilog. So the test bench and the Verilog design together are simulated, and the simulation results, which is timing diagrams and could be other reports and messages. We analyze all of that, ensure that the functionality of the design is correct. If there is a problem with the functionality of the design, we keep iterating that procedure till the design functionality is correct. We make changes in the Verilog design, or if required, we can make changes in the Verilog test bench to make sure that the simulation results are correct. Once the results are correct, we say our design is functionally verified. Once our design is functionally verified, we take only the design, not the test bench, only the design to the backend process, which is synthesis and other backend process. This Verilog design is converted to gate level netlist using synthesis software, or synthesis tools as we call it. At the time of synthesis, we can put some timing constraints on the design. For example, I can say my clock has to work at 100 megahertz. 100 megahertz means in time domain it is 10 nanoseconds. That means I'm telling the synthesis tool that all the paths, logical paths in my Verilog design have to work at 10 nanoseconds or below. If they do that, my timing paths are met. My timing is met. If not, my timing is not met. So the timing constraints can be applied during the synthesis stage. After synthesis, we follow certain other steps: translate, map, place, and route. The map will convert this gate gate level netlist, which uses basic gates, to technology specific components of the FPGA library. Then they are placed on the FPGA device, and the routing is done, means interconnection between the logic gates. After that, there is a static timing reports that gets generated. So any timing constraint that you have put here on the synthesis will be reported here in the timing report. Finally, we generate something called a bit file. This bit file is used to program the FPGA, which is sitting on the board, PCB board. So this FPGA, due to the bit file, will start working like the Verilog code that you have written. So if let's say you have done a Verilog code for a counter, so this FPGA will start acting as a counter. This is the entire design flow for Xilinx FPGA or even Intel FPGAs. The software changes, but the blocks remain the same. Okay, do you understand this flow?
Yes.
So you can note down this flow diagram. It's very important to understand the bigger picture, how it works. So your focus on Verilog design simulation is here in this section. This is called front-end
Mm-hmm.
design. This is called back-end design from synthesis onwards. If you look at the design cycle, so out of the entire design cycle, about 60 to 65% of the design time or the design cycle time is spent on this activity, front-end activity. Writing Verilog code, writing test benches, performing simulation, doing the iterations required. Around 65%
Mm-hmm.
of the time goes here. In the rest, 35% time we cover the other aspects. That's why knowing Verilog,
Yeah.
knowing simulation, writing test benches, all of this is critical because you spend a lot of time in this section.
Yeah. I'm done.
Done. Okay. So this is the end of the presentation. What I'll do for you now is we'll do a demo of the simulation, how it works.
Okay. Okay.
Okay. So this is my simple, let's take a simple AND gate design first. This is my two input AND gate, module my AND. This is my port list, which is in 0 and in 1 is two inputs, each is single bit. Out is a single bit output port. I have a reg call out because I'm going to assign it inside the always block. Always at in 0 or in 1, this is my sensitivity list. Begin the always block. Out gets
Mm-hmm.
in 0 and in 1. So this will give me my AND gate.
Yeah.
And the always block end module. This is my simple two input AND gate design. I've written a test bench for that. Take time scale. That's my first thing in the test bench. 1 nanosecond slash 1 nanosecond. Module my and test with the empty port list. Wire out and reg in 1 in 2. So the way it works is for test benches, whatever inputs are going to be applied to the design will become registers. Whatever outputs coming back from the design will be wires. Why? Because
Okay.
the inputs that are going to the design, I have to change the inputs, and those can be changed inside the initial block or the always block. For
Mm-hmm.
that, for that, those have to be registers. and the output coming back from the design can be connected to the wire because I don't have to change it. All I have to do is monitor it.
Yeah. Okay.
So it can be a wire. The outputs coming back from the design can be connected to wires. The inputs going to the design have to be registers because I have to change the inputs. This is my instance. I am
Mm-hmm.
instantiating my AND gate and doing the port mappings. Then I am going to change the
Okay.
stimulus or apply the inputs for which I use the initial block. Initial begin. There are two inputs, in one and in two. So I will apply various combinations. One one one. After 5 nanoseconds it will be 1 0. After another 5 nanoseconds it will be 0 1. After another 5 nanoseconds it will be 0 0 and some other combinations.
Mm-hmm.
These are my input combinations and the initial block end module. So this is my test bench. So if I go here and where is that? Oh yeah, maybe I can show you from scratch. I have till 4, right? So I create a project. This is ISC. This is 14.2.
Mm-hmm.
14.7 will look exactly same. So I go to project
Okay.
and or I go to this new project here.
Mm-hmm.
So it will open up this. I'm going to call my project and project 5 because I have till 4 in this thing. So I'll call it and project 5. You can call it any name you want.
Mm-hmm.
This you have to change. At this moment, you're going to perform only the simulation. So the device doesn't matter. So you choose one of the devices, whatever is suitable. This is a device. I
Okay.
have a board for this device. So I select this device. Preferred
Okay.
language should be Verilog because you're going to use Verilog as a language. The rest of the things should remain
Mm-hmm.
by default, whatever. Say OK.
Okay.
This project is created. So I need to add my source code, which is a Verilog design and a test bench. I go to project and add source. The source is under this. Go to the directory where your AND gate and the test bench is there. I select them. I say open. Test bench is only done for simulation. My and all means for simulation as well as implementation. Test bench association is only simulation every time because I'm only going to
Mm-hmm.
simulate my test bench. I'm not going to implement it on the FPGA. Say
Mm-hmm.
OK. Now go to simulation tab here. If you see implementation and simulation, by default it is implementation. Go to simulation. You'll see this under my and TB, which is a test bench file. You will find this instance my and, which is a Verilog design. So I select my and test, which is a top level design, expand this and simulate behavioral model. I double click this. Okay, so if you zoom full, you can select all the signals. These are selected. Right click this name, long names. So it will show you which are my test bench signals. These are my test bench signals. These are listed under my and test. So these are two inputs and outputs at the test bench level. And all this action is happening in this area. So I zoom into this area. Now if
Mm-hmm.
this is my timing diagram generated. These are two inputs.
Mm-hmm.
This is the output generated. First, up to 5 nanoseconds, both inputs were high, so output was high. At 5
Mm-hmm.
nanoseconds, input 2 went to 0. So since it's an AND gate, if one of the input goes to 0, output went to 0.
Yeah.
Another 5 nanoseconds, in 2 went to 1, but at that time in 1 went to 0. So one of the input is 0,
Mm-hmm.
output stayed 0.
Mm-hmm.
Another 5 nanoseconds, both inputs are 0, so output stayed 0. At another 5 nanoseconds, both input went high, so output went high. After another 5 nanoseconds, one of the inputs went to 0, output went to 0. So I can say that my design seems to be working okay. or my design functionality is okay. So my design is functionally verified.
Okay.
If you want to add signals from the design, if you left hand side, you'll see instances and processes. So expand that. This is the test bench and this is the design instance called and1. How does it find that from the test bench? This is the label of the instance for the design my and1 is the
Mm-hmm.
label of the instance that will be showed here.
Yes.
If I want to add signals for the design, I select this, right click it and say add to view window. Now these are the names. So I select them, name, long names. So now if you see under test bench, under and1 instance, these are my signals. So these are my design related signals and this are my test bench related signals.
Okay.
Since we already simulated, it doesn't show me the waveform since I've added the signals after the simulation is waveform generation is done. So I have to relaunch my simulation. So it will ask you whether to save it. We'll say no for now. So I can zoom all. This is the area I need to zoom in. So the signals are basically repeated here.
Yeah.
Right, so this is how you can add test bench related signals and design related signals to the simulation window and check if there is a problem somewhere. If it is not working as per expectations, go to the design or go to the test bench where the problem is and make the changes, save that, recompile,
Mm-hmm.
resimulate it, and then relaunch the simulation.
Can you just show me how you went from simulation to the waves? Sorry. I
Okay, I'll close this. So, no. So when I added the source code, I went to simulation tab.
Mm-hmm.
From implementation, I went
Yeah.
to simulation. Under simulation, my
Okay.
test bench and the design under test is listed.
Mm-hmm.
Test bench, in this case, test bench is the top level because it is instantiating this design.
Yeah.
So I select the test bench and I double click simulate behavioral model,
Okay.
which opened
Right.
up this waveform window. And I can select this. I can do a control A, which will select all the signals, right click it,
Mm-hmm.
name and long format, which
Long.
will give me this
Okay.
complete path. Test bench slash. Now this is under test bench. So if I want my design related signal, go to the left hand side instance section,
Mm-hmm.
expand that, and one is my design instance. I select that and I right click it, add to wave window. Select this, signals are selected. I right click them, name long format. So test bench slash and1 slash in zero. This is my design related signal.
Yeah.
So since I've added it after the simulation, I need to relaunch it.
Sure.
You can save this. So now if you want, you can save this if you don't want to do this every time, like add signals to the wave window. For now, we will say no. Later on, we'll see how to do that.
Okay.
So it will just relaunch my simulation, recompile the Verilog code, relaunch the simulation, and regenerate the timing diagram for me, from which I can see this again.
Okay.
Okay.
Yes.
So did you understand how the design and the test bench was added to the project? Then we
Yes.
compiled it, we simulated it, and generated the timing diagram, and then we analyzed the timing functionality.
Yes.
Any other questions on this?
No, not right now.
So next lecture onwards, we would do only practice.
Okay.
There are a couple more lectures left, so we will. I've already given you a few tasks, right, to create a few combinational circuits and I think a couple of sequential circuits.
Yes.
So you can create the design as well as the test bench file for each circuit. Then you can create a project,
Okay.
separate project like we did for each circuit. Run the simulation,
Mm-hmm.
generate the timing diagram, and analyze the timing.
Okay.
For in your case, for MacBook, you Google it how to install Windows application under Mac OS. I think there will be some software which will act as an interface or a middle layer between the two, and that will give you that functionality.
Yes. Okay. I will.
Right? So let's do that and you practice, because if you practice, it will give you more confidence regarding the simulation aspect also.
Yeah.
Okay, so the class today stops here. So the next class will be Friday same time.
Okay.
Okay, see you. Bye-bye.
Thank you.